Okay, so now we're in business. Okay, now, if I remember correctly, we're still in chapter 2. Where did we stop the last time? Did we get into nomenclature? Nope. Structural formulas and models?
I think the last thing we did was calculating the weighted atomic mass.
Oh, okay, so you're talking about this right here.
Right.
Okay, all right. So let me proceed to the next slide. So the periodic table, I'm quite sure we are familiar with the periodic table, what it looks like. And we all know it's a special arrangement of the elements in a periodic table where the rows are called the groups and the periods go across, all right? So, of course, the group has their own designated group number, and the periods also have their group numbers, well, not their period numbers, all right? And the first person credited with coming up with the periodic table is a Russian scientist by the name of Mendeleev. And what he did was that, well, he discovered that if you arrange the elements in order of their atomic masses, after so many elements, you see that there's a repeat in their properties. Now, it's important to note that he used the atomic masses or weights to arrange them. And the reason for that was because the concept of atomic numbers did not come about until after he came up with the periodic table. Because remember, the atomic number by definition is the number of protons in the atom of the nucleus. And the protons were not discovered yet. So basically, the only identifier for the specific elements would be the atomic masses. So that's what he used, right? And he came up with a version of the periodic table. And one interesting thing about what he came up with is that there were some gaps in his version of the periodic table, which represents elements that were not yet discovered, all right? So basically what he could do was predict the type of properties that would be displayed by these elements. And later on, when these elements were discovered, you'll find that there is a great agreement between what he predicted and what was actually discovered as far as the properties of those previously undiscovered elements, right? So just to give an example, well, this is an English version of his periodic table, and you see that there's some gaps right here, here, and so on, which, as I said before, represent elements that were not yet discovered. So he published this periodic table in 1869. The proton was not discovered until early the next century. I don't remember exactly when. So it was sometime before we now understand that the arrangement of the elements in the periodic table is based on not only the number of protons, but the electron arrangements, which, of course, the discovery of the electron occurred afterwards as well, all right? So just to give an example of what was discovered to be the properties of a particular element that was previously not discovered, right? So on the middle column right here, you have the predicted properties of a particular element, which we now call germanium. Back then, they call it Eka silicon, right? And this was in 1871, right? So it was discovered or predicted that the atomic mass of this particular element would be 72. When this element was discovered in 1886, it was discovered that the atomic mass is 72.6 AMU. So as you can see right straight from the top, great agreement between what was predicted and what was discovered. Here, it was predicted that the density of this element would be 5.5 grams per cm cube. Turns out to be 5.47 grams per cm cube. Again, great agreement between what is predicted and what is observed. Color, dirty gray was predicted, grayish white is what was observed. Personally speaking, I think both of them basically mean the same thing, right? So again, agreement is observed there. The density of the oxide was predicted to be 4.7 grams per cm cube. It was discovered to be 4.703 grams per cm cube. Now, in terms of the boiling point of the chloride, they could not predict with a great deal of accuracy the boiling point. All they can say is that the boiling point is 100 degrees or below 100 degrees Celsius. Turns out that the boiling point is 86 degrees when the chloride of germanium was synthesized. And then finally, the density of the same chloride was predicted to be 1.9 grams per mil. Here it's found to be 1.887 grams per mil. So basically, you can see that overall, there is a close agreement between what was observed when germanium was discovered and what was predicted by the periodic table of Mendeleev, right? And this is just one example. There are other examples where we see, you know, the correlation between what is predicted and what is observed, right? So basically things kind of got stuck in terms of understanding why we observe this, because as I said before, the particles like electrons and protons were not yet discovered. And it was only until after that, then we understand now why is it that we have elements occupying particular positions, and it's largely due to the arrangement of electrons around the atom. And that is a topic that we're going to cover later on, all right? So continuing, so this is the periodic table, and most legitimate periodic tables will have two pieces of information along with the symbol of the element. We'll have the atomic number and the atomic mass, which is a weighted average, which is what we discussed last time, right? In the examples that we looked at, all right? So most of the elements in the periodic table are metals, right? In fact, there are three broad categories. There are several categories, but for our purposes now, there are three broad categories of elements. You have metals, non-metals, and then you have a third minor category known as metalloids, right? So most of the elements are metals, right? As you can see, this color, the color scheme here indicates which elements are metals and non-metals and so on. So most of the elements are metals, right? The purple shaded boxes are where the non-metals are located. However, there is, as I said before, a minority group of elements known as metalloids, and they lie exactly on one side or the other of this stepwise line that you see here. Most periodic tables would have that line of demarcation between metals and non-metals. So the metals will be to the left, the non-metals will be to the right, but on either side, immediately of that line, you're going to have some elements like silicon, germanium, arsenic, antimony, tellurium and polonium, and astatine. Those are called metalloids, all right? And the reason why they're called metalloids is because they display some characteristics with metals and others with non-metals, right? So for example, if I were to choose one, let's say silicon, if you were to observe silicon, it's shiny, which is true for most metals. In fact, true for all metals. But it does not conduct electricity as well as metals. All metals conduct electricity very well, but silicon is not exactly a metal, it's a metalloid. So it does conduct electricity, but not as well as in the case of metals, all right? So that's basically it as far as the periodic table is concerned. So let's talk about molecules and formulas. So we all know that molecules are a collection of atoms that are held together by covalent bonds. And the molecular formula is basically a shorthand way of indicating the composition of a molecule, all right? Now, the molecular formula should not be confused with the empirical formula, right? The empirical formula gives the simplest ratio of the atoms of each kind present in the compound, right? So for example, in the case of hydrogen peroxide, this is the molecular formula, right? That tells you that in one molecule of this compound, there are 2 hydrogen atoms and 1 oxygen atom, all right? So therefore, that's a molecular formula. The empirical formula is simply HO because that gives you the ratio between the hydrogen and oxygen atoms. So if you understand that, then you should be able to figure out what the empirical formula for octane, given that the formula is C8H18, all right? So what's the empirical formula based on the molecular formula for octane? If the molecular formula is C8H18, then what's the empirical formula?
Would it be C4H9?
C4H9 is indeed correct. Exactly. All right. So basically, in the case of octane, the ratio between the carbon atoms and the hydrogen atoms would be 4 to 9. All right. So there are other ways of representing a molecule, especially in terms of how the atoms are connected. We can use what are called structural formulas, right? And the example that is shown here is for acetic acid, where the structural formula is given like this, right? That basically gives you an idea as to how the atoms are connected. In fact, a more explicit structural formula for acetic acid, if I can, let me see here. Okay, so in the case of acetic acid, a more explicit structural formula would be CH3, then C double bond O, and then OH. And yet a more explicit representation using the structural formula idea is this right here. Right? So what these formulas tell you is how the atoms are connected. So they're not just telling you how many carbon atoms, how many hydrogen atoms, and so on. It's actually showing you how the atoms are connected, right? And there are other representations that we can use as shown here, right? We call this the ball and stick model. For those of you who have to do organic chemistry, you should be familiar with this when it comes to understanding structure and how structure can influence properties displayed by the substance in terms of physical and chemical properties, right? So basically, the convention is that in the ball and stick model, the black spheres represent carbons and the white spheres represent hydrogen, and then pretty much you can assign colors for other atoms, right? In this case, you have this carbon here bonded to 3 hydrogen atoms, and that carbon is also bonded to another carbon atom, which is at the same time doubly bonded to this oxygen here, which is represented by the red sphere. And then there's a single bond from this carbon to this oxygen here, and that oxygen is bonded to a hydrogen, right? So this is basically showing you the 3-dimensional arrangement of the atoms in this molecule. And again, if you have to do organic chemistry, you're going to see that understanding the 3-dimensional arrangement of atoms in a molecule will influence a lot of things, especially in terms of reactions. Basically, if the molecule is shaped one way and then shaped another way, they will have 2 different reactions under the same conditions. That is something that is very common. And also, you'll end up with different products, right, under the same conditions. So it's very important that you understand the relationship between the structure and the properties that would be displayed by the substance, both chemical and physical properties. Now, over here, what we have is called the space filling model. Now, to be perfectly honest, I don't expect that you encounter this representation in organic chemistry, but if you plan to do higher level research, like in pharmaceutical chemistry and so on, this will become very important, especially when it comes to understanding the mechanism of drug actions, right? Because one working theory in terms of understanding how drugs make physiological changes is that the molecule that is a target molecule will have to somehow interact with what is called an active site. And in order for that to happen, the target molecule must have a particular shape and size, especially with respect to the atom. So therefore, the space filling model helps you to design molecules of the right fit, the right shape, the right size, so that it can dock into the active site of whatever the physiological organism is. And then basically it triggers a process which hopefully, if you're doing research, you hope for these things, results in something positive in terms of health outcomes and so on, all right? So as I said before, in organic chemistry, at least at the undergrad level, you won't be using this. But if you plan to do research in biochemistry, pharmaceutical chemistry, medicinal chemistry, and all that good stuff, then you'll find that this representation will be important. Okay, so let me just skip all this here. So now we're going to get into nomenclature, right? Nomenclature, of course, is basically dealing with how do we name compounds. And there's an organization, an international organization called IUPAC. And this is the acronym IUPAC. And that stands for International Union of Pure and Applied Chemists. All right, International Union of Pure and Applied Chemists, right? And there's a division within this organization that meets ever so often. I don't remember, I think it's every 2 years, if I remember correctly, right? And what they do basically is focus on coming up with rules for naming compounds, right? Now, this is an important function because every year, millions of compounds are either discovered or made, right? And very often what you'll find is that there are some compounds which cannot be named based on the rules that were established before. So therefore, they have to meet to organize the rules so that they can accommodate the new compounds that are discovered, right? So that's basically the role of IUPAC, and more specifically, the particular division in IUPAC, right? So, of course, it's important that we know these rules, right? It's important that we have these rules because, as you can imagine, to come up with unique names for millions of molecules basically would be an exercise in futility, right? So, basically, we have a systematic method which involves the conventions and rules for naming and writing formulas, right? So the first group of compounds we're going to look at in terms of naming them are compounds known as binary molecular compounds. Binary molecular compounds, right? These compounds, binary because they're made up of 2 elements. And because they're molecular, that means that those 2 elements must be nonmetals, right? So basically, these compounds will exist as molecules, right? So let's get into the rules for naming these compounds, right? The first rule is that the name consists of 2 words, the first of which is the complete name of the element that appears first in the formula. The second word or name or second part of the name is the stem of the name of the second element followed by the ending IDE, all right? So basically 2 words, the first word will be the name of the first element in the formula, and the second word will be the stem of the name of the second element ending with IDE, all right? Another thing you need to keep in mind is that the names are further modified by adding prefixes to indicate the number of atoms of each element present per molecule. There are some exceptions, especially to this part, which I'm going to get into, all right? So those are basically the rules for naming binary molecular compounds, all right? Now, this begs the question, which element appears first in the name of binary molecular compounds? Well, in order to predict that, you could memorize this, which I won't expect you to do, right? That gives you the order of the elements in terms of which one would be indicated first in a name, right? A simpler rule to obey in order to indicate or determine which element comes first is to simply look at the element that is farthest down in the periodic table and to the left, right? So if you have 2 elements, you identify their positions in the periodic table. The one that is further down and to the left of the periodic table will be the element that is named first, right? So let's say, for example, you have arsenic and sulfur in a compound, right? The question is, which element will be named first? If you look at the periodic table, any periodic table that you may have available to you, you see that arsenic is below, is in a period below sulfur and to the left of that period, right? So therefore, the answer would be that arsenic would be named first, followed by sulfur, all right? Yet there's another way of determining which element is indicated first, and it's by using the electronegativity values. And that is provided in the same document, which has all those tables which I've posted in Canvas, right? So basically, in that case, what you would do is look at the 2 elements and see which one has the lower electronegativity value. The one that has a lower one will be the one that's named first. So that's yet another tool you can use to indicate which of the 2 elements will be named first in a binary molecular compound. Okay, so with that said, another thing I need to mention too is the use of prefixes. I mentioned it before, but I'm going to go into it in some detail. Now at this juncture, well, firstly, the prefixes are used to indicate the number of atoms of each element, right? And you should be familiar with these prefixes. Mono for 1, di for 2, tri for 3, and so on, all the way down to deca for 10. And that's where we're going to stop. We're going to stop at 10. You can actually go beyond 10. There are some other prefixes beyond 10, but for our purposes, we'll stop at 10, all right? And so therefore, these prefixes must be used. However, there are some exceptions to the use of the prefixes, and I'm going to write them here. So exception for use of prefixes, I should say the exceptions because there are two. For use of prefixes, and the first one is if the first element in the formula, okay, what's going on here? Has only one atom represented, then no prefixes is used for that atom. I hope you can read my handwriting, which is horrible. All right? So what I'm saying here is that if the first element in the formula has only one atom represented, then we do not use the prefix mono for that particular atom in the name of that compound, right? And we can see that in the very first example here, right? In this molecule here, we have NO, right? One atom of nitrogen, one atom of oxygen, right? So because there's only one atom of nitrogen, we do not use the mono prefix for the nitrogen. So you'll notice there's no mono here, right? But for the oxygen, which is the second element, only one atom of that element present. So we use the mono prefix here, and then it ends with the IDE ending, all right? To represent two atoms, so therefore the prefix is di, right? And then you have three oxygens for the second element, so therefore the name of this compound is dinitrogen trioxide, all right? So that's basically how that occurred. Okay, there's something wrong with the Zoom connection here. I don't know what's going on. Oh, shoot, okay. I need to make a reconnection. What happened? Okay, you guys out there in Zoom, I apologize for whatever. Oh, wait a minute. I need to mute this. Okay, yeah, I must apologize for a disconnection that took place. I don't know why that happened. So let me continue with discussing this particular slide. Okay, so if you understood what I mentioned earlier, then you should be able to understand the names of these compounds, all right? So just to pick an arbitrary one, P4O8, 4 phosphorus atoms, so therefore the prefix is tetra, and then phosphorus, and then for 8, octoxide. And let me just say this, there are some situations, and that is mentioned down here. It says when the prefix ends in an A or O and the element names begins with an A or O, the final vowel of the prefix is usually dropped for the ease of pronunciation. So like it says here, yes, sir.
You can no longer, you can't see the.
Oh, my bad. Thank you. Okay, where did I go wrong? Okay, sorry about that, folks. Again, I have to apologize to you guys out there in Zoom. Okay, so let me back up a bit in terms of what I'm saying here. So I was using this example right here, P4O8, right? So 4, the prefix for 4 is tetra, so it's tetraphosphorus, and then octoxide for the oxygen, the 8 oxygens, right? And I was mentioning here that if the prefix ends with an A or O, and the element name begins with an A or O, then the final vowel of the prefix is usually dropped for ease of pronunciation. So let me just explain what that means. So basically, according to IUPAC, the name of, let's say, the last one, tetraarsenic decoxide. You can also call this deca oxide, right? Deca oxide, right? So according to IUPAC, both of them are correct, right? You can say decoxide or decaoxide. You can say pentoxide or pentaoxide, and so on and so forth. So if you do one or the other, you get full credit, all right? So that's basically how we deal with prefixes. Now, there's another exception. So let me just put here exception 2 to the prefix usage. Exception 2. If, how should I word this now? If a binary molecular compound has hydrogen as one of the 2 elements, then no prefixes are used at all. All right? No prefixes are used at all for either the hydrogen or the other element, right? So basically, if you have hydrogen as one of the 2 elements in a binary molecular compound, then you do not use any prefixes. No mono, no di, tri, whatever. So let me give you a couple of examples. We're going to see some more examples later on, but I thought it was important that you understand this at this juncture. If you're given H2S, right? The name of this compound is hydrogen sulfide. Even though you have 2 hydrogens, right? But according to the rules, according to IUPAC, you don't need to indicate the number of hydrogen atoms. You just say hydrogen sulfide. Or if you're given something like HBr, right? The name of this compound is hydrogen bromide. All right? So that's basically how we name binary molecular compounds. If they contain hydrogen, if one of the 2 elements is hydrogen, no prefixes are used whatsoever. All right? We're going to meet hydrogen-containing compounds later on when we are discussing acids, because that's important. These rules are important when it comes to naming these compounds and naming the acids formed from them. Okay, so with that said, let me move on to some examples, right? So this question, well, there are 2 questions. The first of which says, write the molecular formula and name of a compound for which each molecule contains 6 oxygen atoms and 4 phosphorus atoms. Now, to answer this question, we have to deal with the question of which element is named first or indicated first in the formula. And what did I say? How do we decide which element is indicated first? What did I say earlier?
It's the element that is down and left.
Exactly. So you need to look at the periodic table now, and you need to see where oxygen is in relation to phosphorus. And which one is, as she said, further down in the periodic table and to the left of the periodic table? Is it the phosphorus or the oxygen?
It's the phosphorus.
Okay, very good. So you know that whatever the name of the compound is, it's the phosphorus that is mentioned first, right? Now the question says, that the compound contains 6 oxygen atoms and 4 phosphorus atoms. So if we were to write down the formula would be what?
P4.
P4
O6.
O6, exactly. So that would be the formula, right? So what would be the name based on IUPAC rules?
Tetra.
Phosphorus,
Hexoxide.
hex oxide, or hexaoxide. Both can be correct, all right? So tetraphosphorus hexaoxide is the answer, right? Tetra, because you have 4 phosphorus atoms, and then 6, that's where the hexa comes from, and then oxide would be, of course, due to the oxygen. All right, very good. Okay, so that's the first example. What about the second example? Write the molecular formula of phosphorus pentachloride. So let me do it down here. What would be the molecular formula for phosphorus pentachloride? Well,
PCl5.
exactly. Okay, and then in the case of B, they're asking for the name of S2F10. The name. Well,
Duo sulfur.
yeah, but you have to indicate the number of sulfur atoms. How would you indicate that? Di. Disulfur. And then what? What does 10, what's the prefix? For deca?
Fluoroxide.
No, fluoride. Good try though, fluoride. So it's disulfur decafluoride. There are 10 fluorine atoms, so that's where the deca comes from. All right? Okay, any questions about this one? Any questions? Any questions? Okay, let's move along. Okay, so we have talked about naming molecular compounds. Now we're going to get into a discussion of naming ionic compounds. Now remember, ionic compounds are consisting of ions, right? And you can have what are called monatomic ions, and you can have polyatomic ions, right? So let's talk about the monatomic ions. These ions are formed as a result of an atom either gaining or losing electrons, right? So if the atom, oh, and by the way, whether or not the atom gains or loses electrons, there's no change in the number of protons or neutrons in the atom, right? So basically it's the same element, but it will carry a charge in terms of the atom undergoing the change of either gaining or losing an electron, right? Now, if the atom loses electrons, it forms a particle with a positive charge, and these are called cations. On the other hand, if the atom gains electrons, then it will end up with a negative charge, and we call it an anion, all right? So basically, we have cations and anions that can be formed by either the loss or the gain of electrons, respectively, right? Now, one key thing you need to remember is that in an ionic compound, you must have the same number of charges, opposite charges, so that it becomes a neutral compound, right? So basically, as a result, you won't have any discrete units of a particular ionic compound. So to use the example of sodium chloride, there's no discrete sodium chloride units as in the case of molecular compounds where you can have an H2O molecule or a CO2 molecule, right? Where you have basically that discrete unit and you can determine how many atoms are present for each element per molecule. In the case of ionic compounds, you don't have that. What you have instead is something looking like what you see there, where there's a regular arrangement of the ions, and they're so regular that you can actually isolate what is called a unit cell, right? And that unit cell will be repeated throughout the whole growth structure of the particular compound, all right? So very important thing you need to recognize the difference between molecular compounds and ionic compounds. Molecular compounds exist as a discrete collection of atoms per molecule, but in the case of ionic compounds, there are no molecules, right? You just basically have an ordered arrangement of the ions, an example of which is shown here, sodium chloride. And what you'll find is that different compounds, different ionic compounds, will have different arrangements. But basically, once you can identify a unit cell, you can basically see it repeated throughout the structure, right? So this here is basically representing what happens in the case of sodium chloride. The green spheres represent the chloride ions, and the purple ones represent the sodium ions, all right? Okay, so as I mentioned before, the monoatomic ions are formed as a result of an atom either losing or gaining electrons. Now, what you'll find is that the type of ion in especially the A group or representative elements, the type of ion that is formed is largely dependent on which group these elements belong to. So for example, group 1A metals, they all form ions which has a +1 charge, right? So we're talking about lithium, sodium, potassium, cesium, and rubidium, right? Those elements in group 1A, they will lose electrons to form an ion with a +1 charge. Elements in group 2A, right? So we're talking about elements like beryllium, calcium, and so on, magnesium, they will lose 2 electrons to form a +2 charge. Aluminum, which is in group 3A, will form a +3 charge by losing 3 electrons. And then when you get to the non-metallic side, what you'll find is that elements in group 5, 6, and 7 will gain electrons to end up with charges -3, -2, and -1, respectively, all right? So those are just some trends that you can observe in terms of the type of charges formed as a result of an atom losing or gaining electrons. Now, when it comes to the transition elements, things are not as clear-cut, right? Things are a bit not as ordered, or you cannot predict readily based on the position of the elements in that region. In fact, what you'll find is that there are some metallic elements that can form ions of different charges, right? And therefore, we have to indicate what charge is present for a particular ion when these ions are in a compound, right? So just to give an example, copper, let me do it here. There are 2 forms of copper ions. You have copper 2+, and you have copper plus, right? So to indicate which one is which, the name of this one, we call it copper 1. And we put 1 in Roman numerals within the parentheses. And then in the case of copper 2+, the name of this is copper. And then we put Roman numerals 2 surrounded by parentheses. And that's basically how we indicate the charge on these ions, right? And this is important when it comes to naming, because you do need to indicate what type of ion or what the charge is carried by the ion, if the ion can have more than 1 charge. Now, if the ion can only have 1 charge, according to IUPAC, then there's no need for you to indicate a charge, because that is basically being redundant. So for example, in the case of sodium, sodium can only form a charge, an ion with a +1 charge, right? So therefore, the name of this ion is the sodium ion, right? And therefore, according to IUPAC, it would be incorrect for you to do this, sodium 1, right? According to IUPAC, you should not do that, because sodium can only display 1 charge. So the point I'm getting at is that the charge is only indicated if the particular metal element can display more than 1 charge. So like in the case of copper, in the case of cobalt, in the case of manganese and others, where you can have more than 1 charge displayed, then you need to indicate the charge when those ions are present in a compound, all right? And as stated down here in the last line, there are a few of these elements in the transition region where they form only 1 common ion, and some examples here, silver, zinc, and cadmium. And it says here that a Roman numeral is not often used. In fact, you should not use Roman numerals, according to IUPAC, all right? Okay, so let's look at these examples. First question says, determine the formula for, and in the case of A, calcium chloride. So the way to solve this is that first thing I would do is go directly to the tables, right? To look up the formula for calcium and chloride. So in the case of calcium chloride, the formula for calcium, if you look it up, is Ca2 plus, and the formula for the chloride is Cl minus. Now remember what I said. In every ionic compound, the total number of plus charges must be equal to the total number of negative charges. As we have it right now, that's not the case, because here we have +2, here we have -1. So the question now becomes, how do we get the charges to cancel out each other? And the answer is, we have to multiply the chloride by 2, right? So now we're going to end up with 2 negative charges to counterbalance the 2 plus charges. And when you put this together, the final answer is CaCl2. And that's it. So this 2 here becomes a subscript in the final answer. All right? Any questions about that one? Any questions? So how would you do the B part? Magnesium oxide. Again, you have to go to the periodic table. So I need somebody to tell me what's the formula for the magnesium ion. What is the formula for the magnesium ion?
Magnesium 2 plus.
Mg2 plus. And what's the formula for the oxide ion?
O-2.
Or O2 minus, same thing, yeah, right. So basically, what do we need to do next?
Balance.
Just put them together, because it's already, the charge is already balanced, right? So the final answer is MgO. All right? Okay, so any questions about this one? Any questions? Excuse me. Now, in the case of the next example, you're doing the opposite. They gave you the formula, and you have to write down the names, right? So what would be the name for MgS?
Magnesium sulfur.
Magnesium sulfide. Okay, now let me warn you. B is a bit of a trick question. CrCl3, what's the name of that compound?
Chromium chloride.
Ah, I knew you were going to say that. Well, if you had written that in a test or assignment, I would give you 1.5 out of 2 points. Chloride. Because you're missing one important thing. You're missing what?
Is it trichloride?
Hmm?
Is it trichloride?
No. And I'm glad you said that, because I think I forgot to tell you guys this. When it comes to naming ionic compounds, you do not use prefixes. You only reserve the use of prefixes in the case of binary molecular compounds, like the examples that we looked at earlier. But when it comes to ionic compounds, you do not use, tri or di or whatever. All right? So thank you for that question, because I completely forgot to mention that. So what's the missing thing here? What's the missing information here?
The 3,
Hmm?
the 3.
The 3 for the what? Chromium?
Chlorides, 3.
Nope.
Oh, CR is 3 plus, right?
Exactly.
Chromium would have to be C. So would it be chromium 3?
Exactly. Chromium 3 chloride. You need to indicate the charge, right? If you consult the list that I gave you in Canvas, you're going to see that chromium can exist as chromium with a +2 and chromium with a +3, right? So you need to indicate which one it is, right? And as he correctly said, the chromium would have a +3 charge because you have 3 chloride ions, right? Remember, the compound is neutral. If you have 3 chloride ions, that means that the chromium ion must carry a +3 charge. And since chromium can exist as +3 and +2, you have to indicate that in the name. So the name of this compound is chromium 3 chloride, all right? Okay, any questions about this? Any questions? Any questions? Any questions? All right, continuing. Now, this is just giving you some monatomic ions and where they're located. And as you can see, in the case of the elements in the A part of the periodic table, they all basically produce ions which carries a charge. So you don't have, there's an exception here. Tin, let me write this down here. Tin can have +2 as well as +4, right? So you can have SN4 plus and SN2 plus, and the same is true for lead. Lead can exist as +2 and +4. So these two are exceptions in terms of the fact that tin and lead can produce ions of different charges, but they're outside of this region right here. A lot of the ions in this region can display more than one charge when they form ions, and some are shown here. I talked about the copper 2 plus and copper plus, cobalt 3 2 plus, cobalt 2 plus, Fe3 plus, Fe2 plus, and so on. And there are even more down here, which is not indicated, all right? So that's just giving you some locations as to where these particular ions are located in the periodic table, all right? Now, let's talk about naming binary ionic compounds, right? So 2 elements, but in this case, one is a metal and the other one is a non-metal, right? And basically the way we name them first is that, hold on, let me see what we have here. Okay, so the first thing you need to recognize is that the compound must be neutral. So therefore, the total number of plus charges must be equal to the total number of negative charges, right? And the formula unit is basically the simplest unit that can exist in terms of the ratio of the cations and anions, which represents one neutral unit. So to write the formula, of course, you need to know the charges present, and then you multiply when necessary to make sure that the charges are equal, and then you put the formula together. Now, when you're going to name them, you have to start off by naming the cation first and then the anion, all right? So those are just some simple rules for naming these compounds. Just to mention a couple of examples, let me get out of this here. And let me do, will this work? No. Let me go to Word. All right, so in the case of, let's say I gave you this. Let's say that I'm asking you to give the formula for magnesium. No, not magnesium, I'm sorry. Suppose I gave you this. Calcium phosphide. And I ask you to write down the formula for this compound, right? So what you'd have to do is go to the table, you look up the formula for calcium, the calcium ion, which is Ca2 plus, and then you look up the formula for the phosphide ion, which is P3 minus, right? So remember what I said, the charges must be equal. So the question now becomes, how do we get the charges equal? That means you have to multiply this by 3, multiply that by 2, and when we put this together, you're going to end up with Ca3P2, and that's it, right? So that's basically how you can write down the formula based on the name. And if you understand that, you should be able to do the reverse. If you're given the formula, you can determine what the name is, all right? So that's basically how that is done. Let me just see what's next. Oh, so now we're going to get into a discussion of polyatomic ions. And polyatomic ions is different from monatomic ions in that the ion itself is a collection of atoms, and that collection of atoms carry a charge, all right? So basically, in terms of the sheer number of those types of ions, what you'll find is that there are many more polyatomic anions, which are negatively charged, compared to the number of polyatomic cations. In fact, there are only 3 polyatomic cations that you're going to encounter at this level. One of them would be, I'm just going to write them up here, H3O+, which is the hydronium ion. Hydronium ion. The other one is Hg2, 2+, which is the mercury 1 ion. And then the last one is NH4+, which is the ammonium ion. All right, so these are the only 3 polyatomic cations that you will encounter at this level. Most of the ions that are polyatomic are anions, all right? Ignore this line. I don't expect you guys to memorize these ions, all right? Because you'll be provided these ions in the tables, right? So you can ignore that line right there. I should have taken it out. And then you may see some other prefixes like hypo and per. Basically, this is in reference to polyatomic ions that contain oxygen. They're called oxyanions, right? Hypo basically means that there's one less oxygen than indicated in the name of the formula, and per means one more oxygen. But you don't need to remember that because, again, these ions will be available to you during your tests and exams. Also, you're going to see the ending of some of these oxyions either ending with ITE or ATE, right? Again, it's in reference to how many oxygens are present. But again, I won't expect you to be concerned about that because, again, these formulas will be given in the tables that I've provided for you. Okay, and here we have a representative list of polyatomic ions. Of course, the one I've provided for you is more comprehensive. But basically, these are some examples of polyatomic ions that you're going to encounter from time to time. All right? Okay, so let's look at these examples. So the first question is asking for you to write down the formula for sodium sulfite. So what you do, of course, is go to the periodic table and look for the formula for the sodium ion, which would be Na+, and the formula for the sulfide ion, which would be SO3, 2-, right? So again, we have to make sure that the total charges will cancel out. So in order to achieve that, we have to multiply that by 2. So when we put this together, the formula becomes Na2SO3, all right? So that's the answer for the A part. For the B part, ammonium sulfate is what you're given. So again, you'd have to go to the tables. You look for the formula for ammonium, which is NH4+. You look for the formula for the sulfate ion, which is SO4 2-. And in this case, again, as in the case of the previous question, we have to multiply this by 2 to achieve charge balance. But however, when you put this together, you have to be careful, right? Because the ammonium ion is polyatomic, right? So when we're dealing with a situation where we have more than one polyatomic ion present or indicated, we put that in parentheses like this, and then we put a 2 outside because we had a 2 here, and then we put SO4, and that would be the answer, right? So the key thing you need to remember here is that if you have more than one of a polyatomic ion indicated in the name, then in the formula, you surround that polyatomic ion with parentheses, and then you put the number outside as a subscript. And that's how you deal with that, all right? Okay, now for the second example, they gave you the names, they gave you the formulas, and they asked you to determine the name. So what do you think is the name of the first one? Exactly. Something that you don't want to drink unless you're contemplating suicide. Um, so sodium cyanide. All right. What about the next one? Again, you might have to refer to the list of ions.
Magnesium.
Magnesium. Magnesium what?
Two.
Nope. You don't indicate 2 because magnesium can only form a +2 charge, right? So again, according to IUPAC, indicating the charge would be redundant, right? So just magnesium would be the first part. What about the second part?
Is it perchlorate?
Perchlorate. And that's it. All right? Okay, any questions about this one? Any questions? Any questions? Okay. Now, here we're going to get into a special group of compounds, which I don't think you'd have met before. These compounds are known as hydrates, right? And the thing about hydrates is that if you look at the formula for the compound, there's an ionic part to it, and then you have water, a certain amount of water per formula unit, right? So basically, when you're naming these compounds, you name the ionic part first, according to the rules that we covered earlier. And then the next part is where you indicate the number of water molecules, right? And the way you do that is that you use prefixes along with the term hydrate, right? So if it's 1 water molecule, then it would end with monohydrate. If it's 2, dihydrate. 3, trihydrate, and so on, all right? And I think I may have an example here. Oh, and by the way, another important thing too. Whenever you're writing down the formulas of these compounds, the ionic part is separated from the water part by a dot, right? So you write down the formula for the ionic part first, then you put a dot, and then you put the rest for the water part of the formula, right? So here are some examples, right? This hydrate, the formula is BaCl2, and then you have a dot, and then 2 water molecules, right? So the name of this compound is barium chloride dihydrate. Barium chloride dihydrate. In the case of this one, CuSO4.5H2O, right? In this case, the name of this compound is copper-2 sulfate pentahydrate, all right? So that's basically how you name these compounds, right? You name the ionic part first, then you indicate the number of water molecules using the prefixes, mono, di, tri, whatever, and then you follow that up with hydrate. And that's basically how you name these compounds. Now, some interesting things about these compounds, right? One of them is that it's very easy to remove the water from the hydrate. All you have to do is heat the compound to 100 degrees. So in the case of copper-2 sulfate, if you want to get rid of the water, all you have to do is heat it, and you're going to end up with CuSO4 plus 5H2O, right? So you heat this to 100 degrees Celsius, and that's how you drive the water off, right? Another thing that you should recognize is that this can be reversed. So in other words, if you start off, oh, by the way, before I get to that, so this is called the hydrate, and the compound without the water is called the anhydrous form. In some textbooks, you'll see them using the term anhydrate. Same thing. So anhydrous and anhydrate both mean the same thing, right? So I was about to say that another interesting thing about these compounds is that this reaction can be reversed, right? So if you start off with the anhydrous form, you add water, you're going to get your original hydrate, all right? And yet another interesting thing about these compounds is that in some cases, the change in terms of removing water involves a change in the color. So in other words, the color of the hydrated form will be different from the color of the anhydrous form. And that is seen in the case of copper-2 sulfate pentahydrate. The color of this compound here is blue. and the color of the anhydrous form is white. All right? And that is what is seen in this picture right here. Basically, this is the hydrated form, blue crystals. If you heat it to 100 degrees, then you're going to get the white anhydrous form, right? And as you can see here, somebody was adding water to the anhydrous form, and look what happens. It gets back to the original blue color, which is the hydrated form, all right? Now, there's some cases where there's no color change, right? Like in the case of, let me erase this here. In the case of barium chloride, in the case of barium chloride, dihydrate, all right? This is white, and if you heat it, you're going to end up with BaCl2 plus 2H2O, right? And this is also white, right? However, there will still be a change in the appearance because in the case of the hydrated form, it will appear crystalline, I should say. So you're going to see some crystals of barium chloride present in the hydrated form. However, in the anhydrous form, it's more amorphous and therefore powdery. All right? So even though there may not be a color change that occurs when you heat the hydrate, you will still observe a change in appearance where the hydrated form is crystalline and the anhydrous form is powdery. All right? Okay, so that's basically dealing with hydrates. Okay, what time is it, by the way? Oh, 12 more minutes. Okay, I'm just going to talk about introducing acids and bases, and then I'll stop for the day, all right? Because I have a meeting immediately after this. All right, so acids. We're going to talk about acids and bases. And let me just outline a list of properties displayed by acids. Acids, they tend to taste sour. Now, please, that doesn't mean that in the lab you should be tasting acids, all right? However, there's certain fruits that you would have consumed which contains acid, and that's where you get the sharp sour taste from. So I'm talking about, citrus fruits like oranges, lemons, and so on. And also vinegar, which is used to make salads and so on. That tart or sharp sour taste is due to an acid known as acetic acid, the same acid that we met earlier, all right? So that's one particular property of an acid. The second one is that it may produce a pricking or stinging sensation on the skin. So that's why in the lab, I always insist on students being careful when handling acids. If you get some on your skin, make sure that you wash the affected area with lots of water. A third property is that it turns red litmus, it turns blue litmus red. So this is used as a test for acidity of solutions. And litmus can be in the form of a solution, or it can be soaked on a paper and it is commercially sold. And basically, if you're going to use litmus paper, all you have to do is dip it into the solution. In the case of testing for acidity, you're going to dip the blue litmus paper in the solution. If the paper becomes red, then you know that your solution is acidic. Another property of acids is that they react with the more active metals to produce hydrogen gas and some ionic compound, right? So the active metals would be metals like sodium, lithium, potassium, calcium, magnesium, and so on. Those metals will react with acids to produce hydrogen gas and an ionic compound. And then the last property here is that acids will react with bases, thus losing their acidic properties. And this is called a neutralization reaction. And what is supposedly happening, and I say that because this is not true in all cases, but basically if you react an acid with a base, both compounds will lose their properties. The acid will lose its acidic property, the base will lose its basic property, and the resulting product will be neutral. But let me just say that that is not going to be always the case. And if you go on to General Chemistry 2, you're going to learn the reason why, which I won't get into right now, all right? So those are the list of properties of acids. As far as bases are concerned, they taste bitter. Again, please do not taste anything in the lab to find out if this is true. They feel slippery or soapy on the skin. Now, the reason why this happens is because bases in an aqueous solution produces hydroxide ions, and hydroxide ions will react with certain compounds that is secreted by your skin to form, believe it or not, soap. So therefore, the reason why it feels slippery is for that reason, all right? The third property here is that it turns the color of red litmus blue, right? So it does the opposite in terms of the litmus paper test in the case of acids. And the fourth property here is that they react with acids, losing their basic properties. So this is in reference to the same neutralization reaction which I discussed with respect to acids, all right? And okay, so I'm going to stop here for today, right? Because I don't want to start this topic and then stop in the middle of it. Now, based on what we have covered, let me, before I let you go, I'm going to tell you what questions you should try in the assignment number 2. Let me bring it up here. Okay, so let me publish it now. Okay, so based on what we have covered so far, you should be able to complete okay, so you should be able to questions 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so let me see here. Yeah, 12. Questions 1 through 12, right? I want you to try those. If you have any questions or if you're encountering any difficulty while doing them, please feel free to contact me, right? Office hours, oh, okay, Miss Anwar, let me make sure it's published. It's published here. Oh, okay. I forgot to publish this here. Ouch. Okay, Miss Anwar, you should be able to see it. No, all right? So, as I was saying, I'll be in my office today from 2 to 5, and also tomorrow's what? Thursday? I'll be at the Citrus campus, but we can communicate by Zoom, and I'll be here on Friday from 2 to 5, all right? So if you have any issues while doing those questions in assignment 2, then feel free to call me about that, all right? Okay, so that's it for today, folks. So I'll see you guys on Friday. Yes, ma'am.
To get my safety quiz from you.
I didn't,
You
Yep.
mentioned stopping by during office hours to pick it up,
yeah,
to like see how it did.
yeah, so I'll be in my office from 2 to 5, so if you want to pick it up then,
Okay.
yeah.
I just had a question about assignment 1.
Mhm.
When uploading it, all I did was I took a picture of it and then I created that file as a PDF.
Right,
Is that okay?
yeah. Mhm.
It was super blurry though.
Okay,
I-
that can be an issue.
So I was able to compress it so the quality's a little bit better. I sent a little comment when I uploaded it just to if it was an issue. I have the physical copy of it as well.
All right, if you submitted it already, I'll check it out and see
Okay.
what it's like.
Because if anything, I have like the physical paper.
Right,
If it have
all right, no problem. I'll check it out and see. If anything, I'll contact you about it. Yes, ma'am.
Just wondering when the first test was gonna be, if you knew yet. I was just curious, sorry.
I think on the syllabus, I think it said next week, but I think I'll have to postpone that date.
Okay,
Yeah, so, but I'll let you guys know at least a week, right, at least a week ahead of time.
okay, perfect.
All right.
Thank you so much.
No problem, no problem. Okay, and hold on, let me check your messages here. Okay, so Miss Anwar, hope you have located the assignment, right? Okay, all right, so I'm going to sign off now. So I'll see you guys next, on Friday. All right?